A great application involving powers and roots is the use of the Pythagorean theorem. The Pythagorean theorem says that if you take the square of, the sum of, the square of the legs of a right triangle, that will equal the hypotenuse squared. I thought I'd throw an unusual proof your way to let you see this. Here's a right triangle, and I've labeled the legs of the right triangle. They form that right angle A and B, and the hypotenuse as side C. Pythagoras, when first discovering the Pythagorean theorem, very likely could have done something like this. And I'm attempting to draw here a square off of this leg right here, so I'm attempting to make those sides be equal. And that square would have sides A by A, and its area would be A squared. And then I'm going to attempt to draw a square off of this leg as well, so I'm trying to draw these sides equal. And what I'll have here is a square whose area is B by B, or B squared. This is what Pythagoras may have done. And then Pythagoras drew a square off of the hypotenuse. And its area is, of course, C squared, because it's C by C, and again, its area would be C squared. What Pythagoras may have done is, he or she may have moved this square up into the hypotenuse of the square, and I'm going to attempt to do that now like this. Boy, my lines are poor. But here is B squared put inside here. And then, again, my scale is poor, it's not turning out to be all that great. Then took A and divided it up into 4 triangles, and took each of those triangles and put it into the remaining parts of the C squared. And again, this depends on all of this being perfect squares, which they're not, and my drawing perpendicular lines, which that's not happening. But picture this going inside of C squared, and these 4 triangles going in on the outside, and that's why A squared plus B squared fits into C squared, and that's where the Pythagorean theorem comes from. Given 2 legs, A and B, I want to solve for C. Very simple problem involving radicals. I'm going to substitute these 2 values in for A and B into the Pythagorean theorem. So I have a value for A of 8 that I'm going to square. That'll be 64. A value of 10 for B that I'm going to square. That'll be 100. So this 64 plus this 100 adds to be 164, and it equals C squared. I just need to take the square root of both sides in order to solve for C. That's where the radicals come in. I need to take the square root of this because we know that the square root of C squared is C. Well, if I do that on the left, I have to do that on the right. And here's a couple of thoughts from previous sections. I could break this down into the product of 4 times 41, because 4 is a perfect square. And that's the only perfect square that goes into here. And I could call this 2 times the square root of 41, that's equal to C, or I could let my calculator do the work. And I could just take the square root of 164. And if I did this, the book asks us to round our answers to the thousandths place. If I did this, this would be equal to 12.806, either of those 2 answers. I imagine that the book's going to be looking for this, and likewise our tests. If you're given a leg in the hypotenuse and asked to find the other leg, just be careful, especially in this case. I gave you a radical for one of the legs, a value for that leg that has a radical expression, so be careful when you square that. I want to substitute in for A here 4 times the square root of 5, and I want to square that. And I'll substitute in for B, I'll substitute in for C a value of 10, and I want to square that. I'm going to solve for B ultimately here. When I square this, 4 squared is 16. Remember that the square root of 5 squared is just 5, because it's the square root of 5 times the square root of 5. So this right here is equal to 80. And I have 100 over here, and I'll just subtract 80 from both sides. And I have B squared equals 20. And this is the point where I'm going to take the square root of both sides. So I'll do that here and here, and I'll B equals the square root of 20, or I might think of that as the square root of 4 times the square root of 5, which is 2 times the square root of 5, or I might take my calculator to that and find out that the square root of 20 is 4.472. Number 18 in section 7 of this chapter involving radicals reads like this. A slow-pitch softball diamond is actually a square, 65 feet on a side. How far is it from home to second base? Let's look at that problem. I've got the baseball diamond drawn here, and I'm going to show that it's 65 feet on the side, and I can put it all around that square, if you will. But what I want to know here is how far it is from home to second base, the catcher's throw in a steal. And so what I have to recognize is that there's a right angle over here at first base, anywhere for that matter, but I'm looking at this right triangle here, and I see that I have two legs in that right triangle that are given to me, and I want to find the hypotenuse. So I just need to take 65 squared plus 65 squared and let that equal that hypotenuse squared. And when I do that, I've got 4,225 plus 4,225, and I'll add those up, and I get 8,450. And now I take the square root of both sides, and let's see, I don't think I bothered to simplify this because this was a baseball problem and I wanted to know the distance. And it turns out to be 91.924 feet. I'm rounding to the thousandths place because we've been doing that throughout. That's it. Most of our applications in section 7 involve the use of the Pythagorean theorem, or they involve substituting numbers into expressions that can contain radicals and solving for that unknown variable. The last story problem that I'd like to do in this section is number 24. It reads, a 25-inch TV set has a screen with a height of 15 inches. What is its width? All you have to be sure to know in this case is that when we tell you that you have a 25-inch TV set, that's the diagonal of the television screen, and its height is 15 inches. So all I want you to do is to find the width. This is a leg that I'm looking to find, so call it A, if you will, and I'm looking for A. And I'm going to put 15 in for B and 25 in for C into the Pythagorean theorem, and I'll have A squared plus 225 equals 625. When I square those values, subtract the 225 from both sides, and we'll have A squared on the left and 400 on the right. We'll take the square root of both sides, and we find out that that leg, that other side, is a 20 inch. The width of the TV is 20 inches.